Allow me to welcome you back to the second half of our Chapter 2 course discussing the relationships, opportunities, and synergies that now exist between our clients, IBM and Red Hat, given the tight coupling of our portfolios from IBM Systems, Red Hat OpenShift, and IBM Cloud Paks. In the first module of 5 that we'll cover throughout the second half of the course, we'll look at the hybrid multi-cloud world and what it means to operate within that space. We'll dissect what it means to be multi-cloud as well as hybrid, and how clients today are struggling to work across a myriad of vendors and deployment patterns across on-premises or off-premises and public and private clouds. The reality faced by every large organization, including enterprise today, is the struggle to keep pace of new changes coming from the open source community, innovations around things like containerization, orchestration, machine learning, and artificial intelligence, but balancing that with the need to support and maintain existing legacy applications, critical infrastructure, services, and pipelines that have been built over decades and years, which still need to remain operational, but also need to be able to communicate, dialogue with, and interface with those new systems. For that reason, the combined value proposition of Red Hat OpenShift running alongside of IBM Cloud Paks atop of IBM Systems' rock-solid infrastructure provides clients with the glue and the fabric to stitch together those workers, those workloads, as well as draw in the new aspirations and technologies that are fully open sourced and made available anywhere, so that if you need to move across vendors, across premises, you can do so without risk of lock-in, and so you can make use of existing investments that you might have made in other vendors' clouds, IBM's cloud, Red Hat, or IBM Systems, and still take advantage of open source technology that has been hardened and made secure and ready for the enterprise. So with that, let's dive into Module 1. A favorite example of mine for this phenomena of machine learning classification is a bit of an urban legend, the Russian-American tank identification problem. As early back as the 1980s, Cold War-era academics and computer scientists were employing pioneering machine learning techniques known as backpropagation to correctly identify between Soviet-style tanks and NATO-style tanks using aerial and satellite reconnaissance photography. The challenge was both to correctly identify the Soviet tanks from the other vehicles in the photos, as well as to accurately distinguish a Soviet-style tank from a NATO-style tank. The implications for the military doing so correctly at the height of the Cold War tensions are readily apparent. So what happened exactly, and why did this story develop into such a popular urban legend when it comes to computer classification techniques? Like all good legends, there's several variations to this story, but almost all of them involve the time of day that the Soviet-style tanks were photographed over the course of the experiments. The NATO team did the majority of their testing in the early hours of the morning, using mock-ups and replicas of both NATO and Soviet-style tanks. To test their null hypothesis and create a baseline condition, a photographer would revisit the same sites later in the afternoon, taking photographs of the same locations but without any tanks present. The theory was that the machine learning model would learn to distinguish Soviet-style tanks from the NATO tanks, as well as from other objects that might be present in the baseline or tank-devoid scenes. Initially, there was huge optimism for the model's classification abilities. For unlabeled training data, photographs that contained a mixture of both Soviet and NATO-style tanks, it was able to correctly identify that Soviet tanks were present in the scene. But then problems began to emerge. Testing photographs taken on bright days with Soviet-style tanks present were being classified as having no tanks present at all, despite classification being successful in other scenes where tanks were present. What was the cause for this behavior? The model had identified that the single most reliable feature which enabled it to classify between two sets of photos was the angle of the shadows. Early morning photos with very long shadows produced a result of a tank being present in the scene, whereas mid to late afternoon photos with very short to no shadows produced the result of no tank. So in reality, what the computer scientists had designed was a machine learning algorithm for classifying the time of day, not terribly effective for identifying Soviet tanks. The moral of this urban legend is that machine learning algorithms will always take the Occam razor approach, that the simplest explanation is often the best one. The most effective or efficient predictor for distinguishing between two or more conditions or different training data sets will be the one that the algorithm hones in on first and most often. Unfortunately, that criteria may not be the one that you expect, and it may not yield the type of predictions that you are hoping for. Where are we currently on the road to operationalized artificial intelligence? Currently, there are two driving forces behind much of the AI adoption within enterprise today. On the one hand, there is a rapid acceleration in AI projects that data scientists, analysts, and line of business leaders are pursuing. However, these individuals are often disconnected from the infrastructure and DevOps arms of their business, and therefore projects rapidly become derailed by unexpected costs, poor performance, or lack of scalability. Simultaneously, those traditionally tasked with looking after data models and analytics processes are now having to apply their skills to managing AI, machine learning, or deep learning models as well. Unfortunately, these teams may not necessarily have a data science or machine learning background, and therefore may not necessarily be aware of how these models are maintained or trained. To put it another way, DevOps teams are reaching a plateau where they are no longer able, due to skill shortages or insufficient resources, to keep a pace of the growing demand for AI projects from their business leaders and from their customer base. We therefore are at an inflection point where the business aspirations for AI are outpacing the capabilities, resources, and skills of the teams tasked with operationalizing these projects at enterprise scale. What are the hurdles to be overcome if AI or artificial intelligence is to be operationalized? At its core, the problem is threefold. The first is that businesses struggle to decode their AI. They lack the lineage tracking and governance to enable self-service access to these models and the data that they're trained upon. Likewise, many open-source AI projects lack any security or compliance testing capabilities. All machine learning and AI models are subject to the concept of model drift and data entropy, which is the process by which machine learning and deep learning models become overtrained or over-specialized over time. This skewers performance and accuracy of these models, and being able to detect these fluctuations over time and remedy them if necessary are two requirements for any AI adopter. But ultimately, the business needs to be able to explain the why and how of every recommendation or insight that these models generate. This concept bleeds over into the second challenge that businesses face, which is the lack of trust in their AI systems. The black box nature of machine learning and deep learning models and how they're trained means that businesses cannot always rationalize or dissect how an AI system reaches the conclusions that it does. The models produced by AI services need to have traceable, bias-free outcomes if any business is to implement them for production or be able to trust them to run their mission-critical business processes. If you have trust in the efficacy of your models, it becomes very possible to build a business case for future investment in these technologies and for broader adoption of AI across your business. The third challenge is the issue of the skills gap. Enterprises pattern their applications and services on repeatable, consistent practices in order to grow them at the scale required by larger organizations. Likewise, to justify investment in new technology, the business needs to demonstrate the value to the widest swath of workforce as possible. Technologies that only benefit deeply technical personnel, for example, have far less value than technologies that rapidly accelerate the productivity of even non-technical workers. Ideally, these technologies also need to be able to integrate cleanly with the existing applications and business processes without significant rework or refactoring of established systems. So why do so many organizations struggle or even avoid making the leap directly towards AI-driven projects and applications? It harkens back to the example of machine learning classification between NATO and Soviet-style tanks that we touched upon earlier. Machines need to be able to reason, plan, and predict. They need an understanding of the physical world, the digital world, the way that people work, and the way that people think. In order to be effective and to generate meaningful predictions, the machine ultimately needs a human in the loop. Without common sense and subject matter expertise, a machine will throw on blinders, much like a racehorse would, and barrel down to the shortest path available to it to infer understanding from incomplete or imperfect training data. The result may be a model that is able to predict or classify, but may not classify what you intended it to do, or may not produce results that make sense. But infusing subject matter expertise, as well as your own company's data into these models, is something rife with challenges. Your goal may be to make them more effective and their predictions to be more meaningful, but there are challenges to be solved at the software, hardware, and organizational levels. First and foremost, the infrastructure that we run our businesses on today is markedly different from the computing environments of 50, 25, or even 10 years ago. Mission-critical operations are no longer running on a single machine inside the walls of your data center. Instead, services and applications are running across multiple machines, often multiple data centers and a variety of different vendors. A consequence of this reality is that the infrastructure and hardware is more fragile than it once was. As you move from a single machine or a mainframe running your critical workloads, you now need to adjust to a distributed cloud computing framework. And naturally, you need to be prepared for the downtime, latency, or other unforeseen hurdles that go along with distributed environments. The second challenge is a consequence of the fragility of the distributed system itself. As the applications and services move into more distributed environments across multiple machines and multiple vendors, you naturally need to replicate and move code across each of these environments. This introduces multiple versions and locations for your vital apps and services, and naturally your business will do its utmost to ensure consistency across each of these environments. But guaranteeing that code changes, security patches, and maintenance is applied equally and consistently across each of these environments is not a trivial task. As a result, your software is insecure, or at least less secure than it would be inside of a single computing environment, from exposure to security vulnerabilities or bugs resulting from new releases or patching. And lastly, as a result of these two other complications, your services are increasingly complex to manage. Operations teams struggle to patch, maintain, and scale your business applications to meet the growing demand. Individuals within your organization need to be trained or reskilled for each new environment, vendor, or technology that you introduce. If you're working across multiple vendors, it's very likely that each vendor's environment will have a slightly different user interface or pattern of working that requires teams to adjust before they can become productive working with that environment. Without a consistent, homogeneous environment to pull things together, any expansion of your services or applications will require new skills to be onboarded before you can really begin to measure a return on investment. So what are some solutions to these problems that we've just discussed? You need to rapidly deliver updates using open source tools and technology in a way that allows your applications to remain portable and mobile across both environments and different vendors. You want to simplify the process of application development with self-service access to all of your services, tools, frameworks, and knowledge workers available within the same integrated environment. A unified platform allows you to standardize your skills across teams and subject matter experts and your development pipeline against a single consistent pattern. The result is less time needed to onboard new individuals, shorter ramp-up time for new projects, and faster time to value for your investments. You need to break apart monolithic legacy applications into modern microservices architectures. This reduces the maintenance time and costs, as well as mitigates the risks that come from overly complex or unwieldy software. Doing so will simplify critical processes such as version control of code, the consistency of patching and maintenance, as well as provide a unified approach to how you publish future applications. The notion of hybrid multi-cloud isn't a buzzword, and it's not a new approach to marketing an old line of products, but rather it's a practical and pragmatic way of looking at the way most businesses are approaching, or will soon be approaching, information technologies. Namely, the reality that nearly every business will have investments across premises, a true blend of on-premises and off-premises deployments that we tend to call hybrid cloud. And secondly, that most businesses will be purchasing their technologies and services from multiple vendors, not just a single vendor, and this is something that we term multi-cloud. Therefore, in order to bridge the three challenges to AI adoption, the friction between enterprises' infrastructure, software, and organizational structure, you need a hybrid multi-cloud approach that unifies these complex, distributed systems into one integrated architecture. So how does your organization design an architecture that's enabled for hybrid multi-cloud, and what does that enable you as a business or a customer to do? On-premises, for the sake of simplicity in our example, might be thought of as our private cloud environment. On-premises sources might include infrastructure such as IBM Power Systems, scale-out and accelerated systems like the AC922. It might also extend to include IBM AIX or IBM I Power Systems. Off-premises, again for the sake of our example, might be thought of as IBM's public cloud environment. Of course, in actuality, a public cloud environment might also contain a blend of dedicated and private clouds. But to keep things simple and to help differentiate between our off-premises and on-premises environments, let's just assume that the off-premises environment in this case equals a public cloud. This might include a multitude of vendors' clouds including IBM Cloud, AWS, GCP, Microsoft Azure, or others. Collectively, these categories represent your investment in infrastructure, spread across multiple premises in a hybrid fashion and across multiple vendors in a multi-cloud approach. From the infrastructure layer, let's move up one level higher up your stack to the enterprise's ecosystem of virtual machines, containerized applications, and APIs. Of course, no two businesses will keep an identical mix of these services and applications. Your composition might only contain virtual machines, as an example, where others may have a more evenly distributed amount of containerized apps and VM or virtualized apps. But likely, businesses are dabbling in, or perhaps even heavily invested in, multiple forms of these apps and services, even for running mission-critical production workloads. One important thing to note here is that each of these apps and services requires an operating system and a common set of services. However, the dependencies that virtual machines have on these is quite different from the dependencies that a containerized application might have, which are altogether different from the applications that are driven by programmatic APIs. Keep all of this in mind, as this will become important as we move away from the generalized view into a more specific real-world implementation of this architecture. Finally, at one level higher up the stack are the advanced capabilities that your organization or enterprise aspires to achieve. These capabilities might include artificial intelligence, computer vision, hyper-personalization of user experiences, or more bespoke services tailored specifically to your unique business challenges. In order to realize these capabilities, you need to solve the challenges of the two previous layers, the infrastructure and software challenges, but also the organizational challenges of wrangling all these components together across hybrid multi-cloud domains. So what does this look like in a real-world example? If we strip away the architecture layers of the previous slides and hone in on one of the advanced capabilities or aspirations mentioned before, we can see practically how an enterprise might achieve these goals with the help of Red Hat and IBM. We've talked a lot about artificial intelligence so far, but that's certainly not the only reason organizations are in need of holistic, hybrid multi-cloud architecture. Another indispensable capability that business needs along their journey to cloud is the ability to modernize their application stack. In other words, they need a way to move from more complex monolithic applications that are designed to run on a single machine towards more lightweight microservices-based applications that are suited for distributed computing environments. With that goal of application modernization in mind, how can we begin transforming our business to achieve that? First, let's look at your infrastructure. Like most organizations, your IT department stack is multi-cloud and multi-vendor. Recall the generalized view we looked at previously of an enterprise's ecosystem stack, consisting of virtual machines, containers, and APIs. In a realistic setting, the way these applications and services are distributed amongst your enterprise environments are much more nuanced and complex. IBM AIX and IBM I systems are running on LPARs, or logical partitions. On-premises environments in your private cloud might be running on a weighted percentage of virtual machines and a smaller number of containerized applications. Conversely, your off-premises environments on public cloud could be running a blend of virtual machines, containers, and RESTful API-based applications that are communicating over HTTPS. Remember what I said previously about the complexity of wrangling these various domains and deployment models together? Consider that in addition to the various premises and vendors that these services and applications run across, with each of these comes a different set of operating systems and dependencies. AIX-based LPARs are running on a different operating system than IBM I-based LPARs. These are quite altogether different from the virtual machine-based and containerized applications that your on-premises and off-premises cloud environments are also running. You can tremendously benefit from standardizing on Red Hat Enterprise Linux, or RHEL, which is today by far and away the most popular enterprise operating system in the marketplace. Very likely, your enterprise organization is already running RHEL somewhere within its stack. If so, you may have already invested in Red Hat OpenShift, which is providing a single integrated development platform for deploying and orchestration of both your virtual machines and containerized environments within one platform. But there remains one issue. How do all these different deployments of applications and services and code coordinate with one another? Red Hat OpenShift is providing your off-premises and on-premises cloud environments with the tools needed to develop cloud-native, microservices-based applications that meet the application modernization requirements that our organization aspires to. But how do you modernize LPAR-based applications and enable coordination or compatibility with your OpenShift-based applications? The solution depends on the unique blend of capabilities stemming from IBM and Red Hat's combined portfolios. Mainly, the deep integration between Red Hat OpenShift and IBM Cloud Paks. In essence, each of these IBM Cloud Paks are tailored for a specific set of capabilities and use cases. There are IBM Cloud Paks for data, applications, integration, automation, multi-cloud management, and much more on the way. A particular interest to us in this scenario is the Cloud Pak for multi-cloud management. AIX and IBM I-based LPARs are managed via a common set of services in our architecture, mainly Power VC and CAM, or Cloud Automation Manager. CAM is also embedded within the IBM Cloud Pak for multi-cloud management. Together, CAM and Multicloud Manager provide the glue that enables coordination and compatibility of your applications across these premises and different vendors. At this point, you may be wondering why you need both Power VC and CAM to enable coordination and communication between these various apps and services. At the time of this recording in the third quarter of 2019, OpenShift and IBM Cloud Paks are not cross-compatible across different infrastructure architectures. For example, an OpenShift deployment on x86 will be managed as a separate cluster from an OpenShift deployment on Power Systems. Being able to unify these two deployments into a single cluster from a management and deployment perspective is coming in 2020 as the Red Hat and IBM portfolios are more closely aligned following acquisition. But even in 2019, there are workarounds to this siloed approach, mainly CAM and IBM Cloud Pak for multi-cloud management. If you were designing a single application to work across all these environments, being able to deploy it in each without refactoring code at all between environments, you would do so by authoring it as a single multi-cloud image. For example, a containerized application might house two images, one authored for an x86-based architecture and a second image authored for Power-based architecture. That singular container, housing both images, could be deployed across either x86 or Power-based infrastructures without needing adjustment to the underlying code of the application. IBM Cloud Pak for multi-cloud management would then be able to consistently run and operate this application across both an OpenShift cluster deployed on on-premises Power Systems as well as an OpenShift cluster deployed via off-premises x86. Similarly, CAM and Multicloud Manager will be able to coordinate across your AIX and IBM I-based Power Systems applications as well. Collectively, this combination of technology solves the challenge of hybrid multi-cloud architectures. Support for managing heterogeneous or mixed architecture clusters within a single control plane is coming soon. IBM Cloud Paks need to support Red Hat OpenShift version 4.2 and up to provide uniformity of control across both x86 and Power clusters from a single portal. By 2020, IBM intends to support mixed Intel x86, Power, and Z clusters. Until we achieve that parity, there are workarounds available, which we've described here. At a high level, or level 1, a containerized application can have API pointers to underlying, or level 2, image definitions. The images at level 2 may include both a separate Power-based container image and an Intel x86-based container image. The level 1 abstraction provides the API pointers to both the Power-based and x86-based architecture images, which are both housed within the same containerized environment. Customers can achieve this today through a combination of CAM for managing your virtual machines and IBM Cloud Pak for multi-cloud management for managing your container-based applications. Both CAM and the IBM Cloud Pak for multi-cloud management are both in this case running on OpenShift. Cloud Automation Manager creates application templates and defines service compositions for both LPAR-based and container-based virtual machine applications. It then uses the open source technology known as Terraform for deployment to any public or private cloud infrastructure, as well as the standard Helm charts for consistency of operations. LPAR-based applications are typically developed on IBM Power, AIX, or IBM I systems. CAM allows for both LPAR-based applications and container-based applications developed, for example, with OpenShift, to exist within a single catalog of multi-architecture enabled containers. This allows customers to avoid needing to buy new servers or having to undergo the costly and time-consuming process of refactoring existing applications. Customers can take their existing Power, AIX, IBM I, and Linux-based VM applications as they are and consolidate them into a single catalog experience, all available within IBM Cloud Pak catalog. From this integrated catalog, customers can then deploy and manage applications within a common self-service interface that seamlessly aligns workloads to optimize infrastructure. The goal is to modernize your applications one at a time, incrementally. Whether you want to deploy those applications to infrastructure you already own or to a public cloud to take advantage of the consumption models available there, you can utilize OpenShift and IBM Cloud Pak for multi-cloud management to achieve exactly these goals. A variety of consultative, on-demand skills and app accelerators are available for those that are navigating the journey towards hybrid multi-cloud. IBM Cloud Discovery Workshops provide a use case as well as a defined roadmap, whereas IBM Power Cloud Design Workshops help to grow skills, infrastructure planning, application modernization, and more. And finally, IBM Systems Lab services provide high-value applications that are uniquely customized to your business needs. As well as the techniques, best practices, and design patterns that are being discussed in this presentation, the Austin Client Experience Center is also offering individual client accounts an in-depth e-meeting for IBM Systems Power Cloud solutions. You can schedule subject matter experts from IBM to discuss with your client IBM's hybrid multi-cloud strategy, as well as other offerings from Power and Red Hat that can help to meet those clients where they are in their journey towards cloud. For the latest product roadmap and availability details on the offerings discussed in this presentation, please follow the link on your screen or click the link in the charts provided to you. Hopefully you found that module informative, and at this point I expect you're hungry and eager to move on to modules 2 through 5. But before we do that, I want to touch on a few of the key concepts that we drilled and honed in on in this module. The first and foremost being that Red Hat OpenShift and IBM Cloud Paks provides an unparalleled platform that reaches across all of your different silos, be it from data science to application development to multi-cloud management, and pulls those together into a unified architecture that from the perspective of your users, developers, and builders looks like one cohesive ecosystem. And that's very important when we consider the three personas that we've discussed throughout today's presentation. The first and foremost being the application builder, who's tasked with modernizing existing LPARs, virtual machines, towards a more modernized microservices architecture driven by containers, orchestrated by Kubernetes, and again made available through their OpenShift environment and catalog. And from that point in time, you may want to pull in additional capabilities from data science, machine learning, artificial intelligence, in which case the Cloud Paks for applications and the Cloud Paks for data really come together nicely within that OpenShift ecosystem. And finally, for unifying separate environments as well as separate operating systems, you may have certain clusters that are heavily weighted towards virtual machines and others that are running more of a blend or a mix of containerization and VMs and others. You can use the Cloud Pak for multi-cloud management to seamlessly interoperate across all these environments. And keep in mind that as a portfolio between Red Hat and IBM becomes more closely linked and unified in the coming months, we'll see additional opportunities to manage across all these environments with one single pane of glass view. Now with that, let's jump on to Module 2.